So I'd like to thank each and every one of you personally for attending this talk. It's called Get Rich Quick with Beast WebSockets and Networking TS. My name is Vinnie Falco, and I'm the founder and president of the C++ Alliance. It's a nonprofit that tries to advance the interests of C++. I'm also the author of Beast, which is a Boost library that implements the HTTP and WebSocket protocols. It uses Boost.Asio as its networking layer. You're going to see how that plays into the networking TS. You can visit the repository for documentation and examples. I'd like to say a few words about Boost. It's a wonderful collection of peer-reviewed libraries. Two of its great features are the permissive license, which allows you to do almost anything that you want. And then it has a fantastic review process where experts in the field review the library and they offer feedback to the author, and they determine whether the library is accepted and what needs to happen in order for it to go in. So it results in really high quality stuff. You've probably seen components of Boost go into the standard library. It's great. So if you have a laptop here or a tablet or a phone and you want to browse the source code while I'm showing it on the slide so you can see the whole file, this is where the repository is at. Everything that I'm going to show you compiles and it runs. There's a Docker file in the repository if you want to deploy it to a cloud and run the server that I'm going to show you. Okay, I'm going to have to move a little bit quickly. There's a lot of material to cover here, so it's very unlikely that you're going to be able to pick up everything from just one viewing. I encourage everyone to go to YouTube, watch the video. Every time you watch it, you're probably going to learn a little bit more. This material can be a little bit advanced if you want to go into the deep functionality of it. So that said, so who's ready to get rich? So it's not just a gimmicky title. We're actually going to look at some technologies that have been incredibly successful. And I'm going to do a case study of two programs. One of them is called Agar.io, and the other one is called Slither.io. These are both heavily multiplayer games that run in the browser. And you go up against other people, and hopefully you stay alive. If not, your game ends pretty quickly. Each of these programs was individually authored by one person each. They're free to play. Anyone can open up their browser and go to the website, and they can start playing this game. There's no installation, or it's very easy and accessible to get into. You can play a quick game. So each instance of the game can host hundreds of people at once, so you're going up against a lot of people in this arena. And they brought in, at their peak, $100,000 per day in advertising revenue. So what's the secret sauce? It's a WebSocket server written in C++ that runs in the cloud, and then you have a WebSocket client that runs in the browser. Running in the browser is a great choice. It does a lot of things for you, and I think you're going to see when I show you that stuff that it's pretty great. So in this talk, I'm going to review the two key protocols, HTTP and WebSocket. Then I'm going to show you some concepts in the upcoming networking TS that are absolutely critical. Then we're going to look at some code, which is available online, and it's for a multi-user chat server. You can connect to the server, and you can talk to other people that are there, exchange messages. It looks very nice. And then I'll have a few closing words. So the protocols that we need to care about are HTTP and WebSocket. HTTP powers the World Wide Web. It divides computers up into two categories. You have clients and you have servers. The client establishes a connection to the server, and once that connection has been made, then an HTTP conversation can take place. It starts when the client sends a message called an HTTP request, which has a certain format. The server receives the message and performs some computation, and then it sends back the result, which is called an HTTP response. So these are two types of messages. And then once that happens, the client can send another request, and the server sends another response, and then that process continues until either side decides that it wants to close the connection. An interesting feature of HTTP is that it's transportable by intermediate computers called proxies or firewalls. So you can have a computer in the middle, and it'll relay the message. It understands the HTTP protocol. It can do things like enforce policy, affect the security, disallow certain activities, or shape the traffic according to corporate policies. So that's HTTP. WebSocket is developed as an improvement over HTTP. One of the problems with HTTP is that it's inherently a half-duplex protocol. The server has to wait for the client to send the request before it can take any action. The server can't just send an unsolicited message to the client in HTTP. So WebSocket is developed to ameliorate that problem, and it's what we call full duplex and symmetric. That means in a WebSocket session, either side can send a message at any time without being prompted, and they can send multiple messages, they can do whatever they want. The contents of the message are completely up to the application. There's no predefined format. You could send text, you could send JSON, it could be binary format. It's whatever the two endpoints agree to. Like HTTP, it's transportable by proxies. An interesting feature of WebSocket is that it divides messages up into packets called frames. Each frame has a well-defined length, and a message can have 0 or more frames associated with it. There's 3 special types of messages: close, ping, and pong, which they do what they sound like. They allow you to control the meta attributes of the session. So in order to talk WebSocket, of course, you need to have a connection, but a WebSocket connection starts out as HTTP. So the client connects to the server, and they send a special type of HTTP request called an upgrade request. They ask the server, I'd like to talk some WebSocket. So in that request, you can see it's over here. It's a HTTP GET request, and it has the special fields upgrade and connection, and then some protocol-specific gobbledygook. We don't need to get into that. It has to be there. So that's the request. The target, the URI, here it's chat.cgi, allows the client to differentiate which WebSocket service it wants for the case where the server has more than one WebSocket service on the same port. So the server sees that the client wants to do a WebSocket upgrade, and then if it likes the client, if everything checks out, the server will send back the upgrade response, which is a 101 status code. It means that it's going to switch protocols. And as soon as the server's done sending that response, from that point onwards, all of the bytes that are transferred between those two endpoints are going to be WebSocket protocol. So now they're going to talk WebSocket. So Beast fits into this by providing HTTP interfaces, WebSocket interfaces. One of the interesting features about Beast is that it doesn't try to reinvent the wheel. So when you make a connection to a server using Beast, you don't actually use Beast for that. You use the Networking TS, or you use your Boost.Asio. You use those APIs to establish the connection, and then once you have that socket connected, then you can do some transactions with Beast. Okay, so the Networking TS, you've probably heard about it. It's been 17 years in the making, in reality, and it provides an abstraction for networking so that your program can work anywhere that Networking TS is implemented in the standard library. It comes in 3 flavors: Networking TS, reference implementation, Boost.Asio, and Asio. They're all largely the same. In fact, the source code for each flavor is produced from a single source using a script. The only major difference is where you're going to get the header files, the name of the header file, and then the namespaces can be a little bit different. One major difference is that Asio and Boost.Asio have features that are not yet in the Networking TS and won't go in for the first iteration, such as support for capturing signals. I believe serial ports, not exactly sure about that one. Okay, so I'll show you some basics of Networking TS. We're all going to need to know it because it's coming. The first thing you need to have is something called an I/O context. In order to do any type of I/O, you have to have it. It needs to be there. We've just declared one called IOC. Now we're going to create a socket. So the socket has to be associated with an I/O context. Here's our socket. Now once that socket's connected, we might want to write some data to it. So here you can see we're calling this function called write. I use the net namespace alias to show you that it's Networking TS. The actual namespace might differ depending on the flavor that you're using. You all are smart. I'm sure you can figure that out. So here we're calling write on a socket, and then there's some B there. Presumably that's a buffer, and then it seems to return the number of bytes that it was able to write. So what's the type of B? So we know we need to have some kind of memory area with some bytes. B can't be a simple pointer. That's not enough. So I'm going to show you 2 types that Networking TS provides that are suitable types for B: mutable buffer and const buffer. As the name suggests, these are nothing more than a thin wrapper around a pointer and a size. In one version, the pointer is const, and the other one, it's non-const. So this is really straightforward. There's no mystery to it. It's the equivalent of like a fancy pair with a good name and some accessor functions. So now we're going to write a hypothetical function. We're going to write this function called SendMessage. This function accepts a buffer from the caller, and it sends it on the socket in a special format, which is a header that's calculated from the data. It's fixed in length, and then the payload, which the caller provides. You can see in the function signature, we have the stream, which is some templated type that we won't get into, and then we have the payload, which is that const buffer type that you just saw, that wrapper around a pointer in size. So how would we implement that? Okay, well, here's one way to implement it. We call write, and then we construct the header, and we pass that as a buffer, and then we call write again, and then we pass the payload. So we're doing it in 2 steps. We're writing the header, then we're writing the payload. So that's not such a great idea. And the reason is because I/O operations are very expensive. If you're writing a network program and all that you do is try to minimize the number of I/Os, then by the time you're done, it's probably going to work pretty well. So you're going to do pretty well with it. If you don't pay any attention to that, you might find that it's not functioning very well at all. It'll perform poorly. So it would be nice if we could do that in a single call. Okay, so here's one way we might do it. We're creating an array of 2 elements, and it has those 2 buffers in it. So wouldn't it be nice if we could just call write once and then pass that array, which is a type of range? It turns out you can do that. Here's the signature for the networking TS write function. You can see that it's templated on this thing called a const buffer sequence. So what's a const buffer sequence? Well, it's a type of range that has 0 or more elements, where each element is an actual buffer, one of those const buffers that you saw, a pointer and a size. It needs to be lightweight and copyable. It doesn't own the memory. It just refers to memory that's owned elsewhere. So some other object has to maintain the lifetime of it in order for those operations to work correctly. Beast comes with several different buffer sequence types optimized for various use cases. Here's the actual requirements for a const buffer sequence. This diagram, this is called a valid expressions list. It's a table that shows all the valid expressions on a type that meets the requirements, along with some notes. You can see that a const buffer sequence has 2 nested types, value type and const iterator. Buffer sequence has to be copyable, and then it has our familiar begin and end functions, which you expect to find in a range. And then we have a little special carve-out where we say that const buffer and mutable buffer are const buffer sequences as well. So a special case, those 2 types can be used wherever a buffer sequence is expected. When you dereference the iterator, you have to get something that can give you a const buffer. So whatever fancy range or lazy evaluation you want to do, at the end of the day, each element of that range has to pony up a pointer in size. Mutable buffer sequence is another concept. It's just like the const buffer sequence, except it's writable. Every mutable buffer sequence is also a const buffer sequence. So that's that. Now, how do we use it? Let's say we have a string. We're going to construct a string, and now we want to write it. So we're constructing a const buffer, and we're passing the pointer and size of the string. That's a little bit inconvenient, so Networking TS provides a function. It's called buffer. It'll take the string, and it'll construct that const buffer for us. It's a nice convenience function. Almost every type in the standard library that can be used as a buffer has an overload in Networking TS for the buffer function that you can use to conveniently get a buffer to that thing. So those buffer sequences are nice, but sometimes we need something a little bit different. Here's a function called ReadUntil, which we're calling. This function is a Networking TS function which will read from the socket, and it'll store the data in our buffers until it finds a certain pattern. In this case, a double carriage return line feed. So what's the type of B? We know that it can't be a buffer sequence because buffer sequences have no concept of resizing. It's just a range or a view to some memory regions. So here's the signature for Networking TS ReadUntil. You can see, rather than a buffer sequence, we have this new type called the dynamic buffer. So this is the second important concept in Networking TS. A dynamic buffer is used very often, especially in Beast. So here's what it is. It's a resizable buffer sequence. It's got 2 areas. There's a read area and a write area. And as you can imagine, you read from the read area and you put the bytes in the write area. When you don't know the size of the input and you want to write an algorithm, or you want to invoke an algorithm that can return a variable amount of data, dynamic buffer is a good choice for the signature. Now, this is a concept which means that user-defined dynamic buffers are possible. Again, Beast comes with a nice variety of dynamic buffers that you can use, optimized for various scenarios. I'm going to show you how these dynamic buffers work through code. So here we have a dynamic buffer called A. We're declaring it. It starts out empty. The read and the write areas are 0 bytes. So the first thing we want to do is get some bytes in there. We call a read sum function on our socket, and then you can see we're calling prepare on the dynamic buffer with the number 128. So we're resizing the write area to have 128 bytes of possible storage. And then we're calling read sum. So that read sum is going to hopefully get some bytes from the socket and put it in that write area. And then the number of bytes that it was able to actually acquire is going to be returned. So now we have some bytes, and now we want to make them available, so we call a function called commit on those bytes. Let's say we got 60 bytes. So we had enough room for 128, we only got 60, now we call commit, and that moves those bytes from the write area to the read area. So now they're available for reading. So now we want to process that data. I have this function called process. It processes the data. And we're calling a function on the dynamic buffer called data. This returns a const buffer sequence. Let's say that process only uses the first 40 bytes, and it returns the number 40 for bytes used. So now that we're done with those 40 bytes, we want to get rid of them. We don't want to see them anymore. So we call a function called consume on the dynamic buffer. We had 60, we consumed 40, now we're left with 20. At this point, we could read some more and commit that, or we could deal with those 20 bytes and maybe get rid of them, who knows. So you saw the valid expressions table. For dynamic buffer, I'm going to show you a different form of documentation. This is called an exemplar. It's a C++ declaration that hopefully compiles, or mostly compiles, that contains all the elements that are required for the type. Here we have a prototype of dynamic buffer. You can see it's got some nested types. It has some accessor functions related to the size, various sizes. And then we have the functions that I showed you: data, prepare, commit, and consume. That's dynamic buffer. The next important concept is asynchronous IO. Here we have a call to read sum. This is a synchronous function. That means that when you call read sum, it's going to block until it fulfills its contract. That thread of execution is going to be stuck there until it either generates an error or returns some bytes. But very often we want to write asynchronous programs. They perform better, they scale better, and they're a little more complicated, but we need to do this thing. This is what that looks like. Asynchronous operations in networking TS all start with the word async underscore. Here we're calling an asynchronous function. We're going to read some data into some buffers. And as soon as we call async read sum, that function call is going to return. It's not going to block, and the operation is going to be happening in the background. And we need a way to know when the operation's done so we can look at those buffers. So this is that handler parameter that's there. So what's the type of that? Well, here's what one possibility is. We have a lambda expression with a particular signature, and that lambda is going to be invoked when the read sum operation completes. So async read sum will return, and then at some point, the lambda expression will be called. So what are the valid types for this handler? Well, it turns out the next concept is called a completion handler. Asynchronous operations invoke a completion handler, which is a concept in networking TS. It's an invocable function object that has a particular signature. They need to be moved constructible. The asynchronous operation will take ownership of the completion handler by move constructing it, and it will keep it alive until after it invokes the handler. Here are 3 examples of completion handlers. The first is the lambda, which you've already seen. The compiler will generate the function object for you in some anonymous type with a really long, obnoxious name. And then the second example is a user-defined function object. This is no different than the lambda, except you're just writing it out by hand. It has the function call operator. And then the third example, we have the return value of std_bind, which returns a call wrapper. Again, this is an invocable function object. In this case, the standard library is creating that type for you. So back to our asynchronous example. We're going to call async read sum. That call is going to return immediately. And then sometime later, our lambda is going to be invoked. But maybe you noticed something strange. There's a question mark here. What's the problem? Here, let me give you a hint. So that's a thread. Which thread is going to invoke the completion handler? It can't be the thread that calls async read sum. That would be bad. It would be undefined behavior if the implementation just interrupted your thread at some point. That wouldn't be very good. So networking TS provides something called the basic guarantee. A completion handler will only be invoked from a thread that's calling a member function called run on the IO context associated with the IO object. That sounds pretty obscure. Let's see what it actually looks like. Here we have an IO context object, and we're calling run on it. So what that does is that relinquishes the current thread to the networking implementation. What will happen is that call to run will block, and it'll invoke completion handlers and do things until there's no more work remaining. Now, what if we don't want to give up the current thread? Well, we can give it a new thread. Here you can see I'm constructing a thread, and then that thread is going to call IO context run. But there's a little problem here because I'm creating a temporary variable, and then that temporary is going to be destroyed when the expression is done evaluating. So this is not going to work very well. We need to detach the thread in order for it to be able to continue and outlive that temporary. So we can have multiple threads calling IO context run. Here's what that looks like. This is a little snippet that will create n threads, and including the current thread. So it'll create n-1 threads and call IO context run on that, and then it'll commandeer the current thread and call run on that one. So you'll get n threads out of it. So why do we have all this ceremony with the IO context run? So I like to call this bring your own threads. Networking TS philosophy is not to make odd choices on behalf of the user. So the threads are going to be under your control as the author of the code. You can decide how many of them you want, which determines what synchronization model you're going to use. You can even decide which thread facilities you're going to provide. It could be the standard thread, maybe it's operating system specific calls. You have control over the thread's entry point, so you can do interesting things like wrap it in a try-catch. It's really all up to you. The code that I'm going to show you is single-threaded. Keeps things very simple. You can get rich with single-threaded code. All those applications that I showed you are single-threaded. Each game instance runs in one thread, although multiple CPU cores are used to host multiple game instances on the same machine. But each instance is still single-threaded. There's one piece of information that I'd like to share with you about multi-threaded network programs, and that is the networking TS has, let's call it executors light. An executor in networking TS defines how a completion handler is invoked. The most important executor is the one that's associated with an object called a strand. A strand makes sure that completion handlers will not execute concurrently. So if you're going to write a multi-threaded application, strand is something that you're going to want to look at. It involves additional synchronization overhead, but it's really essential. And in conclusion, with networking TS, there's three very common threading models. The first one, which is what I'm going to show you, is single-threaded. That means only one thread calls IO context run. We don't need to worry about any synchronization since nothing's happening concurrently. It's easy to write, it's fast, but it only has one thread. Then we can have multiple threads calling IO context run. So you're going to get more, you're going to utilize more of the machine's resources, but now you're going to be exposed to synchronization issues, which could be a good trade-off. Finally, the most complex is multiple threads where each thread has its own IO context. So that requires more work on your part. It's more complicated, and you'll need to balance the connections among the IO contexts in order to make that work. But it does offer the greatest speed. It has the advantage of not requiring synchronization in most cases, and it has the highest capacity. Okay, now I know you're itching to see some code. Let's see that code. I'm going to show you a chat server that's written in C++ that uses Beast, and it uses WebSockets, and it allows people to connect and exchange messages with each other. So to keep the slides small and to not have any particular bias towards a version of networking, I've created some handy aliases, some namespace aliases, and some type aliases. The code that's in the repository uses Boost.Asio, flavor of networking TS, because Beast itself is in Boost, and it uses Boost.Asio. So here's little shortcuts. So this server is divided up into 5 major components. First, we have main. Hopefully, everyone knows what that is. Then we have shared state, which is information that every object in the system needs to have access to. Then we have an object called a listener. This is responsible for monitoring the port and accepting incoming connections. And then finally, we have these 2 session objects. An instance of these objects represents one connected user of the corresponding protocol. So here's the shared state. This is very simple. There's 2 pieces of information that we have to have on hand at all times. One is the document root. So the chat server is also an HTTP server. It serves HTML files. It serves images or whatever you want to put there, advertisements if you want to make that money. The doc root is the file system path to those files. Then we have a set of WebSocket session pointers. This keeps track of all the users that are currently connected because we want to do things like send them messages or maybe kick them off. Okay, so how do we implement the member functions of our shared state? Well, we have the functions join and leave. These insert and remove sessions from the container to maintain it as people come and go. And then we have a function called send. So this is the function that's going to broadcast a chat message to all the connected users. As you can see, we're taking ownership of the string that's passed in, and we're creating a shared pointer out of it. We're going to use shared pointers in our application, even though it's single-threaded, because it's a very convenient way of allowing multiple objects to refer to the same piece of data. So we construct a shared string, then we loop over each connected WebSocket session, and we call send on that shared pointer. So then they can send the message to the user. Okay, so that's our shared state, pretty simple. So here's main. There's some command line arguments that you need to use to invoke the server. Besides the address and port, we need the file system path to the document root. So here we're going to decode those parameters. And now we have an I/O context. You got to have that. You're going to see it in every networking program. So once we declare our I/O context, we want to create that listening port so that we can start getting some users and making that money. So I'm calling make shared. I'm constructing a listener object for the port. And then we're invoking a member function called run on that listener. Now notice that we're not storing the return value of make shared in any variable. So what's going to happen is when that expression is done evaluating, that shared pointer is going to be deleted. It's the responsibility of the run member function of listener to make a copy of the shared pointer in order to extend the lifetime of the listener. If we don't do that, then the listener is going to be destroyed, and we're not going to really have much to talk about in main. So we create the listener, then we call IO context run. At this point, the main thread of execution, which thus far is the only thread in the entire program, is going to be blocked on that run. And at that point, Networking TS takes over the thread, and it uses it to invoke our completion handlers. So that's main. Listener, here's the declaration for listener. Now you can see we have some Networking TS types. We have an acceptor, we have a socket, and then we have that shared state. So the first thing we want to do in listener is implement our run function. This is what's called from main. And now we're calling AsyncAccept on that acceptor. As you know, asynchronous functions, they start with the word async underscore, so this is one of them. So we're calling AsyncAccept. This call will be outstanding until it receives an incoming connection. And then it'll invoke our completion handler with the error code, and the socket underscore member variable will hold that new connection. So when our completion handler is invoked, we're going to call onAccept. Now notice that in the Lambda, I'm calling shared from this. So we're binding a shared pointer reference into that Lambda. And what that will do is that will extend the lifetime of the listener object. As we talked about in main, run has to extend the lifetime. So Networking TS is going to take ownership of that completion handler, and as long as the operation is outstanding, our listener object is going to exist. So once we get an incoming connection, we're going to call onAccept. We're going to have an error code. If there was an error, we'll report it, like good citizens. You'll see a message. Otherwise, we're going to create an HTTP session. As we talked about earlier, WebSocket sessions start out as HTTP. So we create our HTTP session object. Once again, I'm using the same idiom. I'm calling make shared to create the HTTP session, and we're not storing the return value anywhere. We're just calling a member function called run. So it's the responsibility of run to make a copy of the shared pointer in order for the HTTP session's lifetime to be extended. So now that we've accepted our incoming connection, that call to AsyncAccept was good for only one connection. So we blew that operation. Now we need to start another one. So we're calling AsyncAccept again. This is the same invocation that you saw earlier. The Lambda does the same thing. So we've created a type of loop here. We call AsyncAccept. That operation is outstanding. When we get an incoming connection, we process it, and then we call AsyncAccept again. And that keeps going until the user terminates the server. So one last note on the listener. We want to know how to report the errors. So there's a special error code called operation aborted. This is what will happen if you interrupt the server. Like, for example, you press Control-C, or you cancel an operation. You're going to get that error in the completion handler. We don't want to flood the log with those, so we just don't bother reporting it. Otherwise, we give them a nice error message. So that's our listener, pretty straightforward. So as we saw, the listener constructs an HTTP session. here's that HTTP session. Now notice, again, we're deriving from enable shared from this. We're managing our HTTP session with a shared pointer. And now we have more variables. We have the socket associated with the session. We have a buffer, which Beast needs. And then we have our shared state, which has the document root. And then we have a variable that will hold the incoming HTTP request. So when we construct the session, we call run on it. And now here's a Beast function called HTTP Async Read. So this will read an entire HTTP message. That's right, it's that simple. The message will be stored in the rec underscore variable. And then once we have the complete message, it's going to invoke our completion handler. In this case, it's a Lambda. Just like before, we're binding shared from this into the Lambda. So the lifetime of our HTTP session object is going to be extended at least until the completion handler returns. So normally when you program with classes, you explicitly call the constructor to create your object, and you call some member functions, and then you explicitly destroy the object. Here, things are a little bit different. In this code, the default behavior is for objects managed by shared pointers to be destroyed unless you extend their lifetime manually, which is what we're doing by calling shared from this. You're not going to see any explicit destruction of objects in this code. Instead, what you're going to see is that the lifetime is extended when it needs to be. So this model is very easy to program once you understand how it works, and then you'll never have a problem with objects not living long enough or living for too long and having memory leaks, which is a common source of problems with asynchronous programs. So that's our HTTP session run. We're going to read an HTTP message. Once we get a complete HTTP request, the function onRead is called. So first we check to see if the client decided to close the connection, and then we're just going to shut down the socket. Notice how we just return. As I said before, the default behavior is for objects to be destroyed when they're managed by a shared pointer unless we extend the lifetime. By returning from this function without making a copy of the shared pointer, we're going to guarantee that the HTTP session is going to be eventually destroyed when the completion handler is destroyed. Otherwise, if there's an error, we report it. And then, if you recall earlier, I said that WebSocket sessions start out with an HTTP upgrade request. So this is a Beast function, isUpgrade. It checks if the request is a WebSocket upgrade. If it is, then we want to create the WebSocket session. So by now, you're pretty familiar with this idiom. We construct a shared pointer, an object managed by a shared pointer. We call run on it, and we give ownership of the request to the WebSocket session so we can look at it and figure out what it wants to do. And then we return. By returning, we avoid extending the lifetime of the HTTP session object, guaranteeing that it's going to be eventually destroyed. Now, what if it's not a WebSocket upgrade? Well, our chat server is also a complete HTTP server. We want to be able to serve files from the document root. So if it's not a WebSocket upgrade, then we want to call this function called handle request, which will handle the request as a normal HTTP request. It'll check to see if the file is in our document root, and it'll serve it. Hopefully, it won't allow the user to exploit any vulnerabilities with putting like ... in the path. Make sure you don't do that if you're on a live server. We're not going to go into that function. It's very long. You can look at it in the code. It's in all the Beast examples. But this function returns an HTTP response. And that response can have different types depending on what's in the request. Now, in C++, a function can really only have one return type. So handle request can't use the return channel to return the object. Instead, it invokes a function object which you pass in, and it'll pass that response that it wants you to send in its parameter. You can see I have a lambda which has auto as the parameter. So that's going to be a generic lambda, and the lambda is responsible for sending it. So in order to send it, we put it into a shared pointer so that we can extend its lifetime as long as the operation is active. And then we call a Beast function async write. So async write writes an entire HTTP message. You give it to Beast, and it'll send it, and it'll take care of it. And then when it's done, you know that the message went out. Again, we're binding a copy of the shared pointer to the HTTP session into our lambda. And once that HTTP message, the response has been sent, then we're going to call our onWrite function, which gets called when the operation is complete. So at the end of the onWrite function, we're reading another request. Once again, that's that loop that we talked about earlier. We read a request, we send the response, then we do the read again. So that's going to end in one of three ways. Either the client's going to close the connection, they're going to get an error, or they're going to do a WebSocket upgrade. Otherwise, they're going to keep getting files served. So now we're down to the last class, the WebSocket session. This is the moneymaker here. This does the thing that we want the server to do. It's the chat. So you can see we have some variables, a buffer. This is a dynamic buffer. Flat buffer is a dynamic buffer. It's going to hold the incoming message. Then we have something called a WebSocket stream. So in the HTTP session, you may have noticed that the functions to send and receive HTTP messages, these were simple free functions. That's because HTTP at its lowest level is pretty much stateless. WebSocket's more complicated. There's state information that has to be there, so we need an object to represent that state, and that's what the WebSocket stream is. Beast provides that class for you, and it manages all the boring protocol details. So that's our WS variable. Then we have our shared state, which has our list of connected WebSocket sessions. And then we have a queue for our outgoing messages. So one of the interesting things about Beast, the philosophy of don't make odd choices on behalf of the user. The WebSocket stream can only send one message at a time. To allow it to send more than one message would require making a decision. How do we queue those messages? And then we would have to answer the question of what allocator to use, what data structure to use. And no matter what I pick in that implementation, someone's going to be disappointed. So rather than making that choice, Beast pushes that responsibility onto the caller. So you're responsible for implementing your own queue that's going to be optimized for your own needs. OK, here's our WebSocket session. When we launch the session, we take that HTTP upgrade request, and we just pass it to Beast. We call this function called AsyncAccept. It's an asynchronous function. It's going to look at the upgrade request, make sure that everything about it is kosher. It'll send back the proper response. And then once our completion handler is invoked, now we know we can start talking WebSocket. We're going to call a function called onAccept. You can see, again, we're binding shared from this in there. By now, you're pretty familiar with that idiom. So after we accept the WebSocket connection, if there's no error, we call join on our state. So if you remember, that's going to insert the session into our list of active sessions. We don't want to insert it before the handshake is done, because then we might end up sending a message to a client before the handshake's complete. Who knows what that would do? So now we're OK to insert them into that set. Now we want to read a message. They're going to send a chat message. We want to read it. And here's Async Read. This is a WebSocket stream function. Notice how the interface to asynchronous functions, they're all very similar. We pass our buffer in, which is what's going to hold the result. And then we have our completion handler. Just like before, we call shared from this to extend the lifetime of our WebSocket session. And once we get a message, we call onRead. If there was an error, we report it. Otherwise, we want to send that chat message to everyone who's connected. You saw the send function in the shared state. It calls send on each WebSocket session. And then once we're done sending that message, we want to get rid of it in the buffer. We don't want it there anymore. We want to get a new message into the buffer. So we call Async Read again. This is that loop that we were talking about. We read a message into the buffer. When that completes, we send it to everyone, clear out the buffer, and then we call read again. So that's pretty straightforward. How do we send? So this is the most complex function. When we send a message, we're sending a shared pointer. If you remember, our shared state puts the string into a shared pointer. The first thing we do is put it into our outgoing message queue. This will keep that string alive. No matter how many people are referencing it, now we make sure that since we're looking at it, we have a reference to it. It's not going to go away. We need to check if we're already writing, because as I said earlier, Beast only allows one write operation at a time. So if we're already writing, we need to just return and wait for that thing to complete. Otherwise, if we're the first item in the queue, now we call async write. So this is the Beast function that sends a WebSocket message. You can see we're calling the buffer function on the front of the queue after it's dereferenced. So that will convert a string into a const buffer. And then again, we have a completion handler, which will be invoked after the message is done sending. And we're going to call onWrite. So this is that loop again. In onWrite, we report the error, if any. We erase the message that we just sent. If it was the last reference, if it was the last shared pointer reference, it's going to get deleted. And then if there's more messages to write, we call async write. Again, that's the loop. So now we're going to keep on sending messages until there's nothing left in the queue. So here's the last main function, fail. Here we've got two messages that we don't want to report. Operation aborted, you saw earlier. But now there's a new message called closed. So as I said earlier, WebSocket has three special messages, close, ping, and pong. Close means that the client wants to shut down the connection. It's an orderly shutdown. And Beast will report that as a closed error. So we don't want to report that to the console. We don't want to flood the console. Otherwise, if it's a legit error, then we'll print it. So finally, I know what you're thinking. How do we remove the WebSocket session? Well, that's easy. In the destructor, we just call leave on our state. So when there's no more references to the WebSocket session, the destructor will be invoked, and we'll just remove it from that set. Now, if you remember, there's only one thread in this program, so we're guaranteed that nothing's executing concurrently. We don't need any lock. It's all very simple. So that's the server. I know it was a lot, but you can look at the program and you can tinker with it. It works. Now we're going to take a look at the client. Now, the interesting thing about our client is that it's got some graphics. That's right. And we don't need a TS to do it. So here's the client. You can see you put in the URI, and you press connect, and it'll connect to the server. You can put your name in there, and then you're going to see the chat. You can type messages and press send, and you can talk to people, and then when you're done, you can press disconnect. So we're going to whip up this interface using HTML. It's going to be very quick. It's not going to be like C++. We don't need 8 files. It's going to write a few lines. This is HTML. Everyone pretty much understands what that's like. You've got tags that are in the angle brackets. Here you can see some orange text where it says UI and app. That's an HTML comment. We're going to insert our user interface into that part of our file. So there's only a few different controls. This one is called a button. Oh, sorry. This is an edit box. It's the input tag. You can see that there's some name value pairs. Some of them have to do with the size and how it's drawn. But then there's one that's called ID. You can see I've put URI as a string for the ID. So that's like the equivalent of like a variable name. So that's the name that we're going to give that item if we want to refer to it in code. So here we're creating the edit box that lets you put the URI in. Now we have a couple of buttons. Again, we have this ID that gives the thing a name. And you can see there's connect and disconnect. So now we also want to get the user's name so we can put it into the chat. Again, we're using an input. That's an edit box. You can see it's got an ID. So by now you can see the pattern. You have input, you have button, obviously. And then finally we need that big rectangle that shows all the text for the chat messages. So this is called the PreTag. It means pre-formatted. It won't try to wrap. It'll preserve character returns. Again, we have an ID. Messages is its name. And we're going to use that and we're going to refer to it. And then finally we have the place where you actually put in the message and send it. So that's an edit box followed by a button. Again, we have these IDs. Now, this is all very nice, but we've created a user interface that doesn't do anything. And when you press the buttons, nothing happens. All we've done is define how it looks and how it's supposed to react, but not what it does when you manipulate the controls. So in order to do that, we need to write some code, and I need to explain something that's called the DOM, which is not the popular French champagne. It's actually the document object model. So this is a system that allows you, through code, to access every element of that HTML document. If you want to show things or hide them, or if you want to change text, or you want to make something disappear, or change a style, you do that with this thing called the DOM, and that happens through code. So now we're at the coding part of the client. This is the obligatory trigger warning. The code is written in JavaScript, of course. So here's what that looks like. Inside our HTML, we create a script tag and its corresponding closing tag, and everything inside there is going to be this wonderful JavaScript. Now, I'm not going to go into too much depth. You can kind of look at it and kind of guess at what it does. You see new WebSocket. Hopefully, that should be self-explanatory. So yes, in JavaScript, it only takes one line to create a WebSocket connection to a particular URI and then return the object. So you saw what it looked like in C++. This is what it looks like in JavaScript. Don't get jealous. Now, when they press the connect button, we want something to happen. So here what we're doing is we're assigning a function to the onClick property of the connect button. So all that really means, it's a fancy way of saying that when you press connect, it's going to run that function, which is going to connect to the WebSocket at the URI that we're passing in there. OK, so WS is that WebSocket stream. In JavaScript, you can see it has onOpen, onClose. These are like events, and we're attaching functions to them. You can see that when the connection's established, we are creating this text connection opened, and we're appending it to this messages.innerText. So that's that area that shows the chat messages. All we're doing is we're just appending a string. It's that easy to append a string which will appear. It's pretty much painless. And then OnMessage gets called when we receive a WebSocket message. That's what the server sends the client in that broadcast that you saw. All we're doing is just appending the contents of the WebSocket message into the control and then putting a carriage return at the end of it. So that's how you're going to see the messages that come up. If there's an error, hopefully we won't ever see that. I've never seen it. And then if you disconnect, we close the WebSocket connection. Now, the most complicated part of this interface is, of course, where you type your little message in and then you want to press send. So if you click the send button, then we're calling send on the WebSocket object, and it's going to send your name and then a colon and then whatever text that you typed. And then we're going to clear the field. We don't want to have to make them backspace every time they send a message. That would not be cool. Finally, one last detail, we don't want to have to click the button every time. You want to press the enter key. So this is a little snippet of code. When you release the enter key, it will simulate a click on the send button. And that's it for our client. So believe it or not, this slide shows the entire client. So this is a full client that's WebSocket enabled. This is one HTML file that you can find in the repository. This includes the graphics and the user interface. It includes the edit box. It includes the JavaScript code, everything. This is the client. I think that's pretty amazing how small it is. And that allows you to rapidly create things. You don't even need an IDE. You just need a text editor, and then you refresh it in your browser. And you drop the file in there, and you can refresh it, and you can start seeing your program come to life with your HTML. So how are we going to use this to get rich? Well, Agarrio and Slither.io, when they became successful, they sparked hundreds of clones. Everyone jumped on this bandwagon. There's lots of I/O games. There's other programs that are not games that you can find that are out there. So what are you going to write? Well, in the program that I showed you, it's a chat program which sends text messages. But you don't need to send text messages. You could send chess moves, or you could send the XY coordinates of your character as they get through a maze. Or you could send commands to some type of textual role-playing game. You can see here. You could send Scrabble moves. Or you could even have a game like chess where you can also chat with your opponent. Or you can have a lobby where you're chatting with other people that are looking for a game. The chat code that I showed you would be suitable for that. So really the sky's the limit. By writing a program that runs in the browser, you can get that up and running very quickly with graphics. You could even have sound. And you don't have all of the bulk and complexities that you might get if you try to do that in C++. And if you make your program free, then anyone can run it. You're going to get a lot of users very quickly. I don't know what you're going to write. Maybe someone will write Tinder for C++ users. Who knows? One of the questions that I get, which is very common, they ask me, what book should I get? Do you have a website that teaches you? I haven't really found anything that's great. The only advice that I can give is to read the documentation for the networking, read the documentation for Beast, look at the examples, write as much code as you can. The more that you write, the better you'll get. It's going to take a certain number of hours of writing code and making mistakes until you're going to be proficient at it. It certainly took me quite a number of hours. You can ask questions on Stack Overflow in the Slack. That's a great place to ask questions. And if you're in a commercial setting, I think the best way to learn is to have a mentor. If there's someone at your job or you know someone in your community who's an expert in networking, you want to talk to them and have them answer your questions in a more interactive setting. It's going to help you get ahead much more quickly. So that's the conclusion of the talk. I'm really glad that I made it within the time. I was a little bit concerned I had to cut a lot out of this talk. There's obviously a lot more things that I could tell you. I touched upon, just very lightly scratched the surface of networking. We only saw the single threading examples. So here you can see where to get the slides. You can check out Beast, and you can also check out the rest of the Boost libraries. I highly recommend them. I think they're great. So in conclusion, I would like to thank John Cobb and the program committee and all the volunteers who worked tirelessly to put this conference together so that I could bring my ideas and share them with you. Thank you all for coming. That concludes the talk. I do have about 5 minutes to answer questions. If you want to ask a question, I'll ask. Thank you. I'll also be available afterwards in case they need the room. I don't know if there's another session, but that's fine. Would you like to ask a question?
Yeah. So
Sure.
the pattern where you're creating a shared pointer using enable shared from this,
Right.
does it, it repeats so often, and it only works if you created the shared pointer like that for the first time. So probably, does it sound a good idea to create a static create method with the same signature as the constructor, which would return you the shared pointer for all of those?
Page 70. I had the same thought.
I don't understand the question. Is there a question in there?
Yeah, like basically this works because when we created the shared pointer for the first time and then called run on that, I believe it works only if you had already a shared pointer. Otherwise,
He started with
What a
create
mess.
share. That's what got the ball
Yeah,
rolling,
yeah, yeah.
and then everything else under that started using.
yeah, so the question was having a create method and not have the constructor create it.
Oh, you mean like an extra function?
Yeah.
And sure, that's possible.
Okay.
I mean, it's just a matter of style. It's
Okay.
one extra function in the interface, but I mean, to me, they're kind of the same.
Okay.
I was in a rush to put the program together.
Thank you.
Thanks for asking. Next.
Hello, pretty cool.
Thank
I
you.
also have a question about like shared pointers. In your example, and I guess it's a quite common example, you're running like single-threaded, and I guess like you will have lots of atomic, unnecessary atomic instructions because of like shared pointer. Any thoughts on that? Is there maybe like a way to like?
Listen, when those guys were making 100,000 a day, they weren't worried about those atomic operations. You can get rich and waste a few cycles.
Okay.
But to your point, yes, you're right. So atomic operations, they have a cost. It can be pretty considerable. In this chat server, you're probably not going to notice. But if you have like a high performance application, you're going to want to do something about that. So you don't need to use shared pointer. You could use your own smart pointer wrapper that doesn't use atomic operations. And in fact, I think that Peter Dimov has, if he hasn't committed it already, he has some wonderful work in shared pointer in Boost, which provides non-atomic operations, and also a shared pointer that's optimized for single-threaded applications, which does what you said.
LibSTD C++ also allows you to actually like instantiate a shared pointer, which doesn't do that. But I would like to see like something maybe standardized. That's why I'm asking.
I'm not aware of any standard solution that doesn't have reference counting.
Just quick, a second question is like HTTP 2 support. Is there something on the horizon?
It's not really part of Beast. HTTP 1 is mostly stateless. HTTP 2 is something else entirely. It's very complicated. There's a lot of drama and contention around the development of the HTTP 2 standard. I know that I don't think Google has gotten completely on board with HTTP 2. It seems like they have like kind of like their own solution. So I'm a little bit reluctant to invest the massive amount of resources necessary to produce an HTTP 2 implementation when the benefit's not really there yet. I don't really see it. And WebSocket offers a great solution for doing the two-way messaging. Next.
So I was really taken with, by the way, great presentation. I was really taken with the JavaScript WebSocket interface, which was like, make a WebSocket, 4 or 5 setters of callbacks, and then like run.
Yeah.
And that was after about 90 slides of C++. You're implying that we can't have nice things, but can you explain a little bit why we can't have that particular, or can we have it, but we have to build it ourselves on top of Beast, or do we have to build it some other way, or can we not have it for a philosophical reason?
So I think that's a great question. So the question is, why is something in JavaScript to operate WebSockets so small and simple, and then in C++ it's large and complicated? So that you're right about that. It's definitely verbose in C++, and I attribute that to a couple of core reasons. First of all, there's no mistaking it, but networking in C++ is late. We've needed an abstraction for networking for a very long time, and it's taken a while to get it. Every other language has abstractions. JavaScript has a networking abstraction. You can even change the back end and use the same abstraction, but another vendor's implementation. They have a very robust ecosystem of packages and libraries. We don't have that yet. Networking TS is going to be really a game changer, and it's going to allow us to start catching up. And you're going to see more libraries like Beast libraries that are written on top of Beast. And to what you said, we do need people to build middleware solutions that make it easy to do things. Beast's HTTP support is very low level. There's lots that it doesn't do. It doesn't deal with proxies. It doesn't deal with authentication. It really only understands a few of the fields. So we really need more libraries that are going to be built on top of it to handle things so that people don't need to write large, cumbersome programs.
To check my understanding of what you said about JavaScript, you're saying that there is something similar in complexity and low-levelness in JavaScript, but what I'm seeing in your 5 lines is a very high-level bit, but they have the low-level bit.
That's right.
And we have the low-level bit, or we now will have the low-level bit, but we just don't have the high-level bit yet.
That's right.
Do you have any, what do I Google to find out more about the low-level bit in other languages?
Oh, I mean, I think JavaScript has something called Socket.io. I think, I'm not really sure. I don't really know those other languages very well.
Okay. Thank you.
Perfect segue. So my first chat server was using Node.js on the server, using a Socket.io WebSocket, and it had a pub/sub interface also. So when you would shoot messages back and forth, it would automatically on either side say, hey, I want to subscribe to this, and then route it. I assume that was in the WebSocket standard. Is that something at a higher level abstraction that is in the WebSocket standard but Beast doesn't do yet, or is that a JavaScript agreement between the browser and Node.js?
Okay, so the question is, what facilities exist in Beast WebSockets to do group messaging, publish and subscribe? So that's, publish and subscribe is not part of the WebSocket protocol. These are interfaces that are added by the library providers. Beast does not provide anything like that. In my opinion, that goes against the low-level philosophy. Something like that is easily written, and I look forward to people developing those middleware solutions and then battling each other to see which one's the best. Does that answer your question?
So that's a Socket.io thing that was used on
Right, right. Okay, next question.
So I had 2 questions. The first is I noticed that there was a place where you moved a socket object into one of the constructors, and then you then copied the same socket object back into like a read async to reschedule yourself, but you didn't reinitialize the socket in between. I was curious if that's...
Right, okay. So the question is, why did I move a socket and then use the moved from socket later? Okay, that's a good question. So I want to step back and look at move construction and move assignment in general. So we all understand the consequences of move in the place that we're moving to, but often we don't understand the consequences of what happens to the object that we moved from. And the answer is that the language doesn't specify that in general. It's up to each type that supports move to define what is the state of the moved from object. Now, in the standard library, in most cases or all cases, I think the moved from object has a well-defined state. And in networking, moved from sockets are also well-defined. They behave as if they were constructed again with the original constructor parameters.
Okay, thank you. My other question was, instead of using shared pointers and shared from this, when I capture, you usually do like a self equals shared from this. Could I do like a self equals dereference this and copy this into the Lambda instead?
So the question is, can we simply make copies instead of having a shared pointer reference in the Lambda?
Yes.
So the answer is no. Sockets are not really copyable. Beast's WebSocket stream is not copyable. So you have state that really can't be duplicated. So you need to have a reference. You need to make sure that only one object owns the socket or stream, or else you'll run into problems. Does that answer?
Yeah. Thank you.
Okay, great. Next.
I think you mentioned it quickly, but just to confirm, so there is no way by using just the language NTS to do SSL or support client certificate in the networking.
Okay, so the question is, I think the general question is, how do we do SSL in networking?
Sure.
Okay, so that's a great question. So far, my efforts to settle on the right slides has really failed. So I think what I'm going to do is I'm just going to go ahead and just pop out here. Don't look at this. Don't look at the sausage making. And I'm going to go down to, so if you notice, There we go. Okay, so here's our ReadUntil function. So this is a networking TS function, and I didn't go into much detail during the talk, but you'll notice that the first parameter is called a sync read stream. So this is a concept that's introduced in networking TS. Oh, it's over. Oh, okay. Do they need the room? Oh, okay, great. So this is a concept. Any type that meets the concept requirements can be used there, and networking TS will work with it. Beast respects these concepts as well. And you can use SSL stream implementations that are provided by other vendors. Asio has an SSL stream, and all of Beast's algorithms work with SSL streams. When you construct the Beast WebSocket, you can use an SSL stream as its underlying transport.
Okay, sounds good.
Okay, great. Okay, so I think that's it. No more. So if you have questions, I'll be happy to answer them outside